Yeah, he told me you did it. I went back.
That test broke me. That was the first test of my semester. They broke me up. It like shot me out of. Great.
What you do is
Yeah, where's the? I saw for one on here. Oh, yeah.
bro, it's easy.
No, I know exactly.
So
how it
there's-
goes.
M2, V2, minus this stuff, right? Yeah. So then you use M1 equals O1, A1, A.
Don't worry, I'm gonna do it. I'm gonna do it after Fran retires.
And then you plug in, I know that's 17.8. You solved for rho already. You solved for rho because rho was M1 over R. Sorry. Oh. Yeah, so that's how you solve for rho 1, you solve for rho 3, you plug in. This is equal to rho 2, and then let's say G1.
Hey, what's up? Yes. Yeah.
And you plug it in.
Okay. Yeah. I'll. It's usually uploaded by.
To get another G2.
Okay. Yeah. No, thanks for letting me know. Yeah, you can watch it tomorrow.
I did everything. So it's just up on this.
Yes.
That's so fine. You basically did everything.
I want to show right here. I'm going to the other problem.
I see.
Well, I actually finished the first problem completely. Oh, really? And then I had like.
Okay. Yeah. Thanks for letting me know. I mean, I was still. I mean, the solutions are up. So okay.
Yeah.
Sure. And I'll show you all. No. Okay, cool. Yes. Yeah. So I usually upload it the next week. Yeah, tomorrow morning before noon. Yeah. So it's on. So if you go to the campus site, and so if you go to for today's lecture, go to week 6. Yeah, same as.
Yeah.
It's the end of the shock wave, right?
Yeah, right after the shock.
I messed up on the TT. Or TT, there's one of those.
Yeah, Alessandro, how's it going?
When I did my division, I didn't get a number on that one table. I got like 11. That's why I think I messed up by 11. After that, then I got like 1.0.
Good. Hey guys.
Have a good one.
You too. Okay, it's 5:30. Let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today?
Tired.
I know it's been really cold lately. So yeah, definitely, make sure you guys are keeping warm, keeping dry. Because it's really easy to get sick in this weather. So you definitely don't want to get sick, especially at this kind of key point of the semester. So I know a lot of you guys are having midterms and stuff. We have our own midterm next week as well. Okay, so some announcements. I graded homework 2s this morning. And so these, your grade should be on Canvas. I've also uploaded the solutions for homework 2 as well as homework 1. I apologize for homework 1. I thought I had uploaded a solution for homework 1, but I guess I forgot. And so if you're looking for the solutions to homework 2, one place you can find it is you can find it on the week 6 page. And so you can see here, there's a zip folder here for homework 2 solutions, and everyone on Zoom can't see me because I am an idiot. Okay. All right, so if you go to the course website, if you go to week 6, you can download the solutions here for homework 2. We have a lot of files for this week just because we're going over a lot of code. Today, we'll primarily be going over a code today. So, we have that as well. And you can see the solution for homework 1 is right here as well, okay? Or if you want to find them very quickly, you're not sure what week they're posted in, you can check the files folder here. And so if you click on files, you click on the folder called solutions, and then they're here as well, okay? So definitely check out the solutions. In particular, check out the solutions to the written parts, okay? Because that's what's going to help you study for the exam. Okay? And so homework 3, I believe, is due on Monday. So that's the 6th, right? Yep. So homework 3 is due Monday, and so just to make sure that you have that content to help you for the exam, I'm going to post the solutions for homework 3 on Monday night. Okay, so basically, right when it's due, the solutions will be up there as well. Okay. Okay. All right. So the plan for today is to finish up our lecture notes on convection. And so last time we covered 1D convection, and so today we're going to do 2D. Okay? We're going to do a little bit on. We're going to do a little bit of kind of hand calculations just to kind of give you a sense of kind of the style of what's going to be expected on the exam. But then, for the majority of today, we're going to spend, talking about the code. Okay. All right. So we'll talk about kind of the changes that you would have to implement in the code and, how to implement everything as usual. Okay. All right. So I think that's all my announcements. Are there any questions I can answer before we get started for today? Okay. All right. Let's go ahead and get started then. So let's go over convection in 2D domains. Or I should say convection and diffusion in 2D domains. All right, so up to this point, for the last couple of lectures, we've been talking about convection, right? And so remember, the idea of convection is that it represents the active transport of a material through a moving fluid, right? And so in all the problems that we're going over in convection, there's going to be some moving fluid, okay? In 2D, we're still this is still going to be true. So we're still going to have a moving fluid. But the big difference here in 2D is that our velocity now becomes a vector, okay? What I mean by that is our velocity is going to have both an X and a Y component. Okay. All right, and so with that in mind, let's go ahead and write out our governing equation. And so our governing equation looks like the following. So we have K times partial squared phi, partial x squared, plus partial squared phi, partial y squared is equal to u partial phi, partial x, plus v partial phi, partial y, plus Q. Okay. So here what we have is our diffusion term. So remember, anytime you see a second order derivative, most of the time that's going to be for diffusion. Okay. Here we have our convection terms. And this Q, of course, is our source term. And so you can see our equation here has the same structure as our 1D equation, except now we add some additional terms because we're in 2D, right? So we add derivatives in the y. And so the most, I would say the most important quantities to take note of here are going to be these two coefficients, okay? So U here is our x component of velocity. E here is our y component of velocity. Okay. And so together, those two make our velocity vector. And so just like always, our goal in this problem is to basically take this equation and solve for its solution on a 2D domain. Okay. And the way that we're going to achieve that is through using finite differences. Right? And so the process is going to be the same as what we've been following for the last few weeks. And so we're going to take each derivative here. We're going to replace each derivative with the finite difference expression. We're going to rearrange the terms. We're going to do a bit of algebra. And then from there, we're going to get our finite difference equation. All right. So that's just kind of a preview of kind of where we're going for today. So kind of the first thing I want to do today is kind of show you that process of kind of plugging in for the finite difference, working it out, and then getting our equation. Okay. Another thing I wanted to do is I wanted to show you how to actually apply it. So we're actually going to plug in some values in there and actually get some finite difference equations. And I'm going to show you how that actually factors into the matrix as well. And then from there, we're going to spend the rest of the time just talking about the code. All right. Any questions on any of this so far? Okay. All right. So let's go ahead and apply this. Right, so we're going to replace both diffusion derivatives as well as both convection derivatives with finite difference. Okay. Of course, you can ask the question at this point of, which scheme should we use for convection, right? So last time we talked about, if you use a central difference scheme, you have to worry about stability. Or if you use an upwinding scheme, then that's better too. Okay. For now, what I'm going to do is I'm just going to use a central difference scheme for both convection derivatives, because right now we don't know what direction the velocity is going. And so we can't apply an upwinding scheme yet. Okay. So now, for now, we're going to use central difference for both of the convection derivatives. Okay, so let's go ahead and start plugging in. All right, so on the left-hand side of the equation, we have the diffusion derivatives. And so we have K. First, we have partial squared phi partial x squared. So this is going to be phi I plus 1, comma j, minus 2 vi comma j plus vi minus 1 comma j divided by delta x squared. And then we have the second order derivative with respect to y. So that's going to be phi I j plus 1 minus 2 phi I comma j plus phi I comma j minus 1 all divided by delta y squared. Okay. Okay. So this term right here, this is partial squared phi, partial x squared. This here is partial squared phi, partial y squared. Okay. So all I did was just I plugged in their finite difference representations. Then we have the x convection term, so that's u times partial phi partial x. And so what I did was I plugged in the central difference scheme. So that's phi I plus 1 comma j minus phi I minus 1 comma j. Okay, all divided by 2 delta x. V phi I j plus 1 minus phi I j minus 1 all divided by 2 delta y. And then we have our source term qi comma j. All right, so we've replaced all the derivatives, and so now all we have is just an arithmetic expression. Okay, and so the next thing I'm going to do here is I'm going to rearrange the terms and simplify this a bit. All right, so to do that, first thing I'm going to do is we're going to assume, just for the sake of simplicity, we're going to assume that we have the same grid spacing in the x and y direction. And so we're going to assume that delta x is equal to delta y is equal to delta. Okay. Usually that's a pretty good assumption, at least in this class, because that's what we're going to assume most of the time. Then from there, we're going to multiply the entire equation by delta squared, okay, just to eliminate most of the denominators. Okay. Okay. All right, so let's see what happens when we do that. And so we're going to do that, and we're also going to do a little bit of simplifying, not too much, because I want to keep something separate, just because it's going to make the code a little bit easier. But you know, we'll see. Okay, and so if we do all those steps, what we get here, is k times bi plus 1 comma j plus phi minus 1 comma j plus phi j plus 1 plus phi comma j minus 1 minus 4 phi comma j Okay, so that's all the diffusion terms, and so those should look very familiar. And so if you look at the coefficients of 1, 1, 1, 1, and minus 4, that's exactly the same as we had from before with 2D diffusion. Okay. Right, then on the right-hand side of the equation, we have, I'm going to factor out the 1/2 on the bottom, and then the delta comes out on top. So we have u delta divided by 2 times phi plus 1 comma j minus phi minus 1 comma j, okay, plus we have v delta divided by 2 multiplied by vi j plus 1, vi j minus 1. Okay. And then we have our source term, so qi comma j delta squared. Okay. So we're almost there. So we're almost at a point where we can start applying this. And so last thing I'm going to do is I'm going to take every term that's associated with phi and then move those over to the same side of the equation. So I move all those to the left-hand side. Because we know, because based on the way that we set up our linear system, the left-hand side matrix contains all the coefficients for the phi terms. Okay, and so it makes sense that we move them all to that side of the equation before we start, forming our linear equations. Okay, so if we do that, this is going to be our last step. So we have k vi plus 1 comma j plus vi minus 1 comma j plus vi j plus 1 plus vi j minus 1 is 4 phi I comma j, okay, minus u delta divided by 2 phi I plus 1 comma j minus phi I minus 1 comma j, okay, minus v delta divided by 2 phi I comma j plus 1 minus phi I j minus 1. All this is equal to qi comma j delta squared. So what we have here is this is our finite difference equation, or our interior node equation for 2D convection diffusion. All right, so that process that we just went through, that where we started with kind of an original differential equation, we plugged in the finite difference approximations, and we kind of worked through the algebra to obtain something like this. This is basically what I want you guys to be able to do on the exam. Okay, and so on the exam, what I'm going to give you is I'm going to give you an equation just like this. This is a bit different because this is generic, but in reality, we'd plug in values for k, u, and v. Okay, and for delta as well. And so you should be able to obtain an equation like this and then apply it to a mesh, which I'm going to show you in the next step. Okay. All right. Any questions on this? Okay. So let's actually apply this just really quickly. So let's do kind of a very simple kind of 2D mesh. Okay, so we're going to have the following domain. So let me label all the nodes. And so according to our ID equation, which looks something like this. So let's give it some boundary conditions. And so let's say that over here we have phi is equal to 25. Down here we have phi is equal to 75. Here we have maybe partial phi, partial n is equal to 0. And then up top right here we have partial phi, partial n is equal to 10. Okay, so that's our domain. And so our governing equation, let's assume it's something like this. And so we'll have 3 times partial squared phi squared plus partial squared phi partial y squared is equal to 30 partial phi partial x plus 75 partial phi partial y plus 3xy. Okay. All right, so we have our domain, we have our grid too, okay, and we have our governing equation, okay. And so if we assume for this problem, let's assume that our grid spacing delta, we'll assume our grid spacing delta is, we'll say just 0.5, just for the sake of simplicity, okay. So given that information, let's write out the equations for a few of these nodes. Okay. So let's do node 3. Let's do node 7. Let's do node 10. And then we'll do node 15. Okay. Okay. Well, this is very typical, and I literally just made this up kind of on the spot. And so, this is very typical of what you would see on the exam. Okay, so for a 2D problem, I'm not going to ask you to write all 16 equations. That would be just busy work and kind of cruel. And so probably what I'll do is I'll give you an equation, I'll give you a domain with the boundary conditions, and I'll ask you to give me specific equations for specific nodes in that grid. Okay. All right. Any questions on this?
So your delta or partial phi over partial n represents your.
Yes, yeah. So when you see partial phi, partial n, that's always going to be on a boundary of the domain. So those are going to be your Neumann boundary conditions.
And your regular phi in the case like these, they are your.
Those are your Dirichlet boundary conditions. Yeah, yeah. Well, I'll show you how to handle those two and how those show up as equations. Okay. All right. So let's get started with this. So we'll just go in order. So let's do equation 3 or for node 3. All right. So remember, when you're writing these linear equations for these kinds of problems, the first question you have to ask yourself is whether this node is going to be on the interior or if it's on the boundary. Okay. And so for node 3, let's go back to our domain here and let's look for node 3. We can see that node 3 is located right here. Big red circle around it. All right, so based on its location, we can see that it's on the very bottom of the domain, right? And so we can see from here that node 3 is a boundary node. And so whenever you have a boundary node, that means its linear equation, it's not going to be determined by the finite difference equation that we have up here, right? So for a boundary node, its equation is going to come directly from the boundary condition. Okay. And so for node 3 right here, we can see that it borders this boundary, and the boundary condition that we have is phi is equal to 75. Okay. And so this type of boundary condition, remember, where we're directly specifying the value of phi, this is a Dirichlet type boundary condition. And so the equation for a Dirichlet type boundary condition is quite simple. So all we have to do is we take the whatever node number that we have. Okay, so we have, this is going to be node 3. And so our equation is going to be phi 3 is equal to, it's going to be equal to whatever the boundary condition specifies. So in this case, the specification of the boundary condition is 75. So our equation is going to be phi 3 is equal to 75. And that's it. That's all we need for this boundary condition, okay, for this equation. Okay, so before I move on to the next one, I do want to kind of show you how this would fit in to the linear system. Okay, because ultimately, you know, that's the main reason why we're producing an equation for each node, so that we can fit it all together into our left-hand side matrix and the right-hand side vector. So let me go ahead and draw our matrix here. Give myself a little bit more room, because this matrix is ginormous. I don't have room for all of them, but just imagine that there are 16 rows. Okay. And so now that we have this equation for phi 3, that means we can write out the equation for row 3 in the matrix. Okay. Row 3 is going to be this one right here. Okay. And so our very simple equation, phi 3 is equal to 75, we need to incorporate that into this row of the matrix right here. And so to do that, you know, we have to keep in mind that this equation, the way that we obtain this equation is we basically multiply this row in the matrix by this vector here of phis. Okay. And so we need to make sure that the coefficients in this row in the matrix need to match up so that we recreate this equation up here. So that's the equation we want to recreate, is phi 3 is equal to 75. Okay. Because if let me just put in some start to put in some values into this matrix, okay, or into this row, I mean. And so if we have this row A, B, C, D, E, F, G, okay, and we continue on. Remember, when we multiply that row by that vector, okay, basically what I like to imagine is you kind of take this row and you kind of like rotate it around until it matches up with that one there, and then you just kind of add those terms together. Okay, so multiplying that row, what we get is A times phi1 plus B times phi2 plus C times phi3 plus D times phi4 plus E times phi5 plus F times phi6 plus G times phi7 and yada, yada, yada. Okay, so this is going to continue all the way until phi16. Okay. And so remember, I want you guys to kind of remember this because it's kind of an easy point to kind of forget, especially when you're getting lost in kind of the details of writing the MATLAB code, right? When we're defining or when we're specifying the values in the left-hand side matrix, all those basically they're just coefficients for the phi terms for that equation, okay? And so when you're setting the coefficients, you basically need to ask yourself, well, this is the equation that we want, right? So we want this equation phi3 is equal to 75. And so what do the values of A, B, C, D, E, F, G, H, I, J, K, L, N, O, P, what do those have to be in order to recreate this equation with you, okay? All right, and so we go based off that, and we go based off, kind of our generic equation down here, okay? We can see that we need a coefficient of 1 in front of the phi3 term. That's what the equation dictates. And so basically we have a 1 out here. Okay. And so that tells us that in our equation, C has to equal to 1, right? Meanwhile, everything else, A, B, D, E, F, G, all of those are going to be 0 because those don't show up in our equation at all, right? All right, so for a Dirichlet boundary condition, we only have one modification that we make to the left-hand side matrix, which is just the third entry. Okay. One more thing that I'll kind of highlight to you is that because this is the equation for I is equal to 3. Okay, we know that this is the third row in the matrix. Okay. Coincidentally, by making sure that C is equal to 1, we know that the entry that we're modifying, the C right here, is in the third column, right? So third row, third column. So that means that this 1 is being added to the diagonal entry of the matrix. So we have LHS matrix, 3, 3, is equal to 1. Okay. And so when we go to modify our code, that's basically what it means. All right, any questions on this? Okay. So I want to do that just to kind of give you a little bit of background in terms of how we take, how we go from this kind of very simple equation to coefficients in a matrix, because that's an important part to understand when you're writing the code. Okay, so let's move on to the next node. And so the next node is, which one was it? Node 7. Okay. All right, so let's go ahead and locate node 7 in the grid. Okay. And so we can see here that node 7 is an interior node. Okay. And so for an interior node, we know that we're going to apply this equation up here. So whenever, we're going to apply our finite difference equation to our interior nodes. Okay, so let's start doing that. So node 7, interior node. Okay, so let me go ahead and write out the finite difference equation again. So we have k phi plus 1 comma j plus phi minus 1 comma j plus phi comma j plus 1 plus phi comma j minus 1 minus 4 phi comma j minus u delta divided by 2 phi plus 1 comma j minus phi minus 1 comma j minus v delta divided by 2 phi j plus 1 minus phi j minus 1 is equal to q I comma j delta squared. Okay. You don't have to write this down again. It's just a repeat of what's above, but I didn't want to keep scrolling back and forth. So I wanted to kind of see you, or I wanted you guys to see me kind of plug in directly to these. Okay. And so when I say I plus 1 is the right neighbor, then you can kind of see what that looks like. Okay. And so more importantly for this one, we actually have values for k, u, v, and delta. Okay. So k in this problem is equal to 3. U, what was u? U was 30. E was 75, and delta is 0.5. Okay, so let's go ahead and plug in for that. So remember, this is for node 7. Okay, and so we plug in for k. K is going to be equal to 3. So let's go ahead and plug that in. Then we have phi I plus 1 comma j. So I plus 1 means that it's the right neighbor, right? So the right neighbor to node 7, if we go back to the grid here, the neighbor to the right of node 7 is going to be node 8. So we have phi 8 plus phi I minus 1 comma j. And so this is going to be the left neighbor. So the node that's to the left of node 7 is going to be node 6. This is phi 6 plus phi I comma j plus 1. And so this is going to be the top neighbor. So the node that's above node 7, I believe, should be node 11. Yep, node 11. Then we have phi I j minus 1. So j minus 1, of course, is the bottom neighbor. Okay. And so if we take the bottom neighbor from node 7, that should be node 3. Okay. We have -4 times phi I comma j. Phi I comma j is just this current node, and so we have phi 7. All right, so that's the diffusion terms. Okay. Next, we have the convection term. So we have U delta divided by 2. So U is 30 in this case. Delta is 1/2. And so we have 30 divided by 2 times 2. Okay. That's 30 over 4, which is about 7.5. All right, and then we have phi I plus 1 comma j. And so, of course, this is the right neighbor. So this is phi 8. Okay. And then we have phi I minus 1 comma j. So this is going to be phi 6. Okay. And so then we have the v velocity terms or the y velocity terms. And so that's phi I comma j plus 1. So that's going to be the top neighbor. So that's phi 11 minus phi I comma j minus 1. So that's phi 3. Okay. And then we have q I comma j. Q in this case is 3 times x times y times delta squared. So delta squared is going to be 1. Okay. And so for the interior nodes, you're basically going to be applying the finite difference equation. Okay. And so the tricky part is just to make sure that you're plugging in all of the neighboring nodes correctly. So you make sure you get the ID numbers correct for that. Okay. And then from there, it's just kind of a lot of plug and chug. Okay. Any questions on kind of what we did for this step right here? Okay. And so of course, what you would do from this point, or at least kind of what I like to do is I would like to take the left-hand side and combine like terms. Just to kind of make it simple. Okay. And so you can do that. Just in the interest of time, because I want to make sure we have at least half an hour to talk about the code. I'll let you kind of do that part. Okay. The last thing I'll do in this part is to kind of help you compute xi, yj. Okay. So xi or yj, these are the physical coordinates of the of node 7. So the node in question, of course, is node 7. Okay. And so to obtain these, you would have to know the I and j coordinates of node 7. And so the I and j coordinates of node 7 is going to be 3, 2. Okay. We have I is equal to 3 and j is equal to 2. And so if you recall from our 2D diffusion code, the way that we obtain the xi and yj is we take whatever the I coordinate is, minus 1, and we multiply it by delta x. Okay. And yj is going to be j minus 1 multiplied by delta y. Okay. And so for this particular problem, we know, or for this particular node right here, we know I is 3 and j is 2. And we know that delta x and delta y are both the same, and they're both equal to 0.5. Okay. All right, so we plug those in. We plug in I is equal to 3. We have 3 minus 1 is equal to 2, multiplied by delta x. we get 1.0. And then for y comma j, we have j minus 1. If j is equal to 2, then that's equal to 1. We multiply by delta y, and we get 0.5. Okay. And so you would take those results and plug it into that source function, and then you multiply by 3 and divide by 4, and that's what gives you the result. Okay. Any questions on this? Yes.
I just don't get why it's like 1 and 5, because I would expect it to be 3. So is it like the unit vector version of coordinates?
You mean why it's 1.0 and 0.5?
Yeah, instead of like 3 and 2.
Oh yeah, because I and j that's kind of the counting variable, and so that's like the, you know, if we look at node 7 right here, right? And so in order to reach node 7, that's the third node in the x direction and the second node in the y direction, right? So that's kind of its counting coordinate. But in order to plug into the equation, we actually need its physical coordinate. And so then we factor in this thing right here, which is the grid spacing. Because we know that the physical distance in between each node is 0.5, yeah, both in this direction and in that direction. Yeah, so that's what we mean by the grid spacing. Yeah. Good question. All right, any other questions on this part here? Okay, all right, so I know in this problem, you know, we said we do 2 more nodes, we do node 10 and node 15, but I didn't want to just neglect the code because, you know, I wanted to make sure I go through that just so that you can look, just so that you can see it for the whole. Okay, so let me go ahead and switch over to the computer screen here. Okay. All right, and so if you go to the weekly page, week 6, I posted 2 codes for today, and so I posted the code for 2D convection diffusion, finite difference starter. Okay, so that's the starter code. That's what we're going to be working on today. But if you want to see the finished product, the finished code, then that's the second code right here. Okay. But what I'm going to do is I'm going to go through the starter code here and then fill it in kind of interactively so that you can kind of see what's going on. Okay. And so I structured this code a little bit differently. And so I basically filled in most of the code for you. It's just that whenever there is something that I need you to fill in or something that we're going to fill in together, I left a, I left this to do. Okay. So basically if you see to do, so it says to do, not todo. Okay. So to do. That means that's code you need to do. Okay. Okay. All right. So let's start by just looking at section 1 of the code. So section 1 is always going to be to define variables. Right. So I basically, you know, just like before, I've defined all the variables that we need for this code. Okay. So first we have Lx and Ly, and so those are going to be the lengths of the domain in the x and y direction. So that's the physical length of the entire domain. Right. And so we're going to assume that that's just 1. Okay. Then we have nx and ny, and so that's the number of grid points in each direction. Okay, and so what you can imagine, so if you compare it to our example that we just did, for the example that we just did, we only had 4 nodes in each direction, right? So with 4 nodes in x, 4 nodes in y. Okay, so in this case, we're going to do 50 by 50, so it's a lot more. Okay? So of course, that's not a problem we can do by hand. So you know, we're really kind of leveraging MATLAB's power here. Okay, and so after that, we compute the total number of nodes. And so the total number of grid points is just going to be the product between nx and ny. Okay. From there, we compute the grid spacings in each direction. So dx dy, that's just going to be the length of the domain in each direction divided by the number of nodes. Okay, and so nx minus 1, ny minus 1 for dx dy. Next, we computed the left-hand side, or we're creating the space for the left-hand side matrix. And so we're using our typical zeros command. So we say left-hand side matrix is equal to zeros, and tote, comma, and tote. Okay. And so this gives us an empty matrix that has n tote number of rows and n tote number of columns. Okay. And then we created a right-hand side vector where the number of rows in that vector is n tote. Okay. And then from here, what I did was I defined some of the parameters for the problem. And so I defined this parameter called diffusion. And so that's going to be equal to 3. And so this is the same thing as k. Right? I defined the x velocity to be 30. And so that's going to be the same as our u variable in our notes. And then I had this y variable, y velocity is equal to 75. And so that is the convection in the y direction, which is v. Okay. Okay. So remember, I like to kind of write my codes in this way. So if there's something I wanted to change, and so let's say, for instance, I wanted to change the number of grid points. And so let's say I wanted to make it more fine. Okay. And all I have to do is just change this upper section of the code right here. And then everything else is going to update from there. Okay. And so ideally, the way I like to write the codes is that, once you kind of write section 1 and you fill out everything else, okay, everything else, should not be changed. So you can use this code to solve several different problems. The only thing that you would have to change is just this upper portion right here. Okay, so that's kind of my thought process when kind of writing these codes. Okay. All right, so let's go ahead and start writing the code here. So the first section that we come across is this one, where we have to populate the left-hand side matrix. Okay, and so this is going to be for all the interior nodes, and so this is going to be for the for the interior node equation that we went over together in class. Okay, so the first thing we're going to do is we're going to compute the ID numbers, and so we have my ID. So my ID, this is for I, j. Then we have left ID. Left ID is going to be for I minus 1, j. Right ID is going to be I plus 1, j. Up ID, this is going to be for I, j plus 1. And down ID is going to be I, j minus 1. Okay. So let's go ahead and compute their ID numbers. And so my ID, we know, is going to be nx times j minus 1 plus I. So that's just our typical ID equation. So if we're given I, j, then the ID number is going to be nx times j minus 1 plus I. Okay. So let me copy this equation for each of the other IDs, and then let's modify it according to where the neighbor is. Okay. All right, so we do the left ID first. And so for left ID, we replace I with I minus 1. The right ID, we're going to replace I with I plus 1. Okay. For the up ID, we're going to replace J with J plus 1. Okay. And for the down ID, we're going to replace J with J minus 1. Okay. All right, so that should be pretty consistent with our diffusion code. Okay. Any questions on the ID equations? Okay, so that is taken care of. So now let's start filling in the other parts of the code right here. Okay, so let me do this so you can still see that. Okay. So now we have the diffusion contributions. Okay. And so if you look at the notes, I left that our equation in kind of a very specific form, right? And so actually, let me zoom back to the note just so that you can see it really quickly. Okay. I'm coming back. Don't worry. Okay. But I want you to have some context for kind of what I'm going to apply for the coefficients. Okay. And so for this part, okay, remember this part right here, this part came from the diffusion derivatives. Okay. This part came from the X convection. And this part right here came from the Y convection. And so if you notice, if you kind of, if you have photographic memory from like 10 seconds ago, you'll notice that in the loop, I basically created a section inside the loop for the diffusion contributions, from the X velocity contributions, and for the Y velocity contributions, okay? So that's kind of the reason why I left it in this form, because normally what you can do is you can do it all in one, so you don't have to separate them. So you can say that, we have I phi I plus 1 here, phi I plus 1 there, so we can combine them into one, okay? And in later parts of the course, we are going to combine them. But for this one, just because this is our first time, I thought I'd leave them separate so that you can see me kind of adding these contributions, in different ones. Okay. Okay. So with that in mind, let's switch back. So now we're back into MATLAB, right? Hopefully no one's getting motion sick, switching between these screens too much. Okay. Okay, so with that in mind, let's list out or let's write down what these contributions are going to be. Okay. I'm going to do all of these together here. And so for the left ID, up ID, down ID, up ID, okay, for the diffusion contributions, because all of these are going to be the same. And so if you look back in the notes, those contributions are going to be a positive 1 multiplied by the diffusion constant. Okay. So all of these are going to be diffusion, 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 diffusion. Okay. And then the contributions to my ID comma my ID, this is going to be -4 times diffusion. Okay. Does that make sense? Kind of how we got those coefficients for those terms there. So it's a little bit different. And so if you look back at our diffusion code, we had 1, 1, 1, -4. Okay. The reason for that is in our 2D diffusion code, we took that diffusion constant and we divided it through the entire equation. Okay. Here we didn't do that. Here we kind of kept it the way it is, and so we need to factor that in to that side of the equation. Okay. Okay. All right. So all that looks good. So next, let's do the contributions from the X convection. Okay. And so right now we're going to do central difference. And so you can see here, I've written code here for the contribution to the right neighbor, as well as the left neighbor. Okay. And so if you look back at your equation, this is going to be for the I plus 1 term, it's going to be a minus X times velocity times dx divided by 2. Okay. And for this one, it's going to be a positive because we have a minus times a minus, a positive x velocity times dx divided by 2. Okay. Right, and we can do the same thing for y. So for y, it's going to be very similar, but instead of x velocity, it's going to be the y velocity. And so for the up neighbor, this is j plus 1. So this is going to be a minus y velocity times dy divided by 2. Okay. And this is going to be a positive y velocity times dy divided by 2. Okay. All right, any questions on this? We do have to make one additional change here, okay? Because right now, as the code is written, we're going to erase a lot of these terms, okay? Because if you look at kind of the format, or if you look at the syntax for how we're applying the convection contributions, okay? This equal sign basically means that we're replacing that whatever was there before, okay? So right now, we are replacing we're replacing what was there before, okay? Because we're using just the equal sign. And so we need to modify this code a little bit because when we add our convection contributions, we don't want to erase what was there before, right? And so instead we just want to add to it. And so we can do that by applying our update notation. So if we take this and we copy it over to the other side of the equation, we do the same thing here. And I apologize, it's a little bit hard to see because of the spacing. And so when you include both the left-hand side matrix thing on both sides of the equal sign, that basically ensures that we don't eliminate what was there before, but we just add to it. Okay, so this was our update notation, if you remember from our MATLAB review. Okay. And so with those done, we're basically done with the entire with the entire interior matrix. Okay? So the big difference between this code and our 2D diffusion code is that we're making multiple changes, we're making multiple contributions to the left-hand side matrix. Okay, and that's okay. And so we're going to be doing a lot of this together throughout the class. Okay, any questions on this? Okay. All right. So with all the interior nodes done, I think for this example, I should have written it on the note before this. But for this particular example, I'm not applying any source term. Okay. So for now, we're going to say that Q is equal to 0. And so the only thing we have left to do here is to compute the boundary conditions. Okay. And then for this problem, and I should have written this down, so I apologize. And so for this problem, just to make things a little bit simpler, I'm having Dirichlet boundary conditions all around. So we have Dirichlet boundary conditions on every side of the grid. Okay. And so our domain looks like this. And so we have phi is equal to 50 up here. On the right boundary, we have phi is equal to 25. On the left-hand side, we have phi is equal to 50. On the bottom here, we have phi is equal to 25. Okay, so that's the boundary conditions for this one. So, because for this example, I mostly wanted to highlight the changes to the left-hand side matrix. I kept the boundary conditions really simple. Okay, so there are no Neumann boundary conditions here. Okay, so with that said, let's go ahead and fill in this code. I believe that's the last thing we have to do. Yes, okay. All right, so we know that for Dirichlet boundary conditions, we only have to make one modification to the left-hand side matrix, right? And so we know already that this is all going to be 1, okay? So basically anything with left-hand side matrix for a Dirichlet boundary is going to be 1. And this one, first one here, okay? And then what we put in the right-hand side vector is going to be whatever the Dirichlet value is for that boundary, okay? And so we look at this section of the code, this is for the left boundary. And so according to my beautiful serial killer drawing, we can see that that is going to be 50. Okay. That is the boundary condition on the left. We go down here. So for the top boundary, that boundary condition is also 50. We go to the right boundary, we can see that boundary condition is 25. And then for the bottom boundary, this one is also 25. Okay. All right, so the last thing we have to do here is compute our ID number. So let me go ahead and copy and paste our ID number equation here. Okay. And then what I'm going to do for each boundary is I'm going to modify it based on whichever boundary that we're on. Okay. And so for the left boundary, we know that I is equal to 1. And so I'm going to replace I with 1 for this boundary. Okay. For the top boundary, we know that J is equal to NY. And so I'm going to take our usual ID number equation here. And then for J, I'm going to plug in NY. Okay, next for the right boundary, you know that I is equal to nx. And so I'm going to take our usual ID number equation. And then for I, I'm going to plug in nx. And then for the bottom boundary, we know that j is equal to 1. And so I'm going to plug in our usual ID number equation. And then for j, I'm going to plug in 1. Okay. Okay. Let's go ahead and save that. Okay. So I did that fairly quickly, but the boundary conditions, whether you have convection or not, are basically going to stay the same. Okay, so if you have any questions about how to apply the boundary conditions, we went over that kind of in detail in the 2D diffusion section. So definitely check out those lecture notes if you still have questions. Okay, all right. So with all of that done, we should be able to run. So I'm going to go ahead and run the code. Give it a little bit of time because it's a 50 by 50. Okay, and you should end up with a plot that looks like this. Okay. All right. So that is looking good. Right. And so you can see here that we have our Dirichlet boundaries all around, and so everything is everything is being pushed up towards the boundaries because of the velocity. All right. Any questions on this? Okay. All right. And so that is the code, right? And so if you want to see the finished code, that one is here as well. Okay. And so what we did was basically we filled in the starter code, but you can also see the filled in code, everything from here as well. Okay. Okay. All right, so all that's looking good. So let me go ahead and close this. There is one more kind of smaller topic that I want to go over before we close, because this is going to be, today is the last day of content for the midterm, okay? And so I want to make sure that I define cross-stream diffusion for you guys, because I know there is a learning objective on that as well. Okay, so let me go ahead and stop sharing here. Here. Okay. Okay, so let's talk a little bit about cross-stream diffusion. Okay. So cross-stream diffusion is a very unique phenomenon that only occurs with 2D convection, okay? All right. So what exactly is it? We know that in 2D diffusion or 2D convection, our velocity is a vector, right? So the vector has a direction. Okay? Okay. And so that means, we can represent the velocity with an arrow, right? And so if we draw a typical grid, okay? So let's say that we have a typical finite difference grid like this, okay? We can have a velocity, that may be pointing in a direction like this. Okay? So this is a pretty typical case. And so, we have a velocity that's going in usually it's some kind of diagonal direction. Okay? So more often than not, what's going to happen is that your velocity vector is not going to align with the grid. And so what I mean by that is if you look at the grid lines obviously go in the X and Y directions. So they're perfectly horizontal or perfectly vertical. Okay. And so the velocity is usually not going to align with that. And so the velocity, unless it's a very unique case, the velocity is never going to be either perfectly up and down, and it's never going to be perfectly left to right. Okay. And so in these situations, when the velocity is not perfectly in line with your grid, what can happen is you can have basically artificially enhanced diffusion. What do I mean by that? So normally in a regular kind of convection diffusion situation, the amount of diffusion that you should observe is defined by the diffusion constant. Okay? So if you look back at our original equation, remember we had k times partial squared phi partial x squared plus partial squared phi partial y squared is equal to u partial phi partial x plus v partial phi partial y plus q. Okay. That was our original equation. Okay. And so the main coefficient that's determining, basically how strong the diffusion is, or how much diffusion you get, should just be k. Okay. And so in any situation, you're going to have passive spreading, right? So that's what diffusion is essentially, is passive spreading. And the amount of passive spreading or the strength of that passive spreading is determined by k. Okay. But if you have cross-stream diffusion, the k is going to be enhanced. Okay. And so even if you write a code, and so you write the code, you explicitly say k is equal to 3, right? We only want a strength of 3 diffusion. Okay. If you have cross-stream diffusion, your total k, okay, is going to be not only contributed to by the original k, but you're also going to have this false k. Okay, so it's like a false god. Okay, where this false k comes from cross-stream diffusion. So obviously this is something that's bad, right? So you don't want to have, when you set the parameters for the problem, you want those to be the actual ones that you simulate. Okay. But what can happen sometimes is that you can have some weird numerical effects that actually change the parameters of your problem. So this is obviously really bad. Okay. Unfortunately, we don't have time to go into the specifics of why this happens. We'll learn about how to fix this, not now, but kind of later on in the class. But I wanted to introduce this idea. Okay. And I want to tell you the situation where cross-stream diffusion is worst. Okay. So the worst cross-stream diffusion Worst cross-stream diffusion occurs when the x and y components of the velocity are the same. Or I should say their absolute values are the same. Okay. So you can have a negative u, positive v, but if they have the same magnitude, then that's going to cause the worst cross-stream diffusion. Okay. So unfortunately, there's not much we can do to get away from it at this point. We'll learn how to deal with this at a future date. Okay. But just know that that kind of is a problem. Okay. It's an open problem that we'll fix later. All right. Any final questions on this? Okay. All right. So that's it. So after today, this is it for midterm 1. Okay. So this is kind of the cutoff for the content. And so on Monday we'll cover something new. We'll start to talk about unsteady problem and what exactly that means. And then Wednesday we'll take our midterm. Okay, so remember Monday I plan on recording the review video. You can also look forward to the solutions to homework 3 on Monday as well. Okay, and I will see you then. Right. So thank you guys for coming today. I hope you guys have a good weekend. If you have any questions while you're studying, please don't be afraid to reach out to me. Okay. I will say I am going out of town this weekend, so I won't be able to respond to you until Sunday night, but I will try to get back to as many people as I can before I go to sleep. Okay. All right, so have a good weekend, and I will see you guys on Monday.
That's right, right? But
Yeah.
they were like canceling out. Yeah. Because you unraise your one.
So remember, for this one, I want you to use an upwinding scheme for the convection. So I can see right here that we're doing a second difference, right? So because the velocity is negative, I want you to use a forward difference scheme. It'll be phi, instead of phi 3 minus phi 1, it'll be phi 3 minus phi 2. Get that?
Velocity is negative.
Exactly, yeah. So the coefficient in front of the this first order derivative, so that means the